This scene deals with the subject many fathers find so difficult.
Welcome to Podcast V0.1, where we break down the latest research and tools for curious engineers. Imagine your Kubernetes cluster automatically picking the perfect mix of cloud servers, not just more of the same type you already have, slashing costs by potentially up to 87% and drastically reducing resource waste compared to the standard cluster autoscaler. Sounds pretty good, right? Well, a recent paper explores how using a mathematical technique called convex optimization could make that a reality. Let's set the stage. Many of us use Kubernetes for orchestrating our containerized applications. A key piece of that ecosystem is the Cluster Autoscaler, often called the CA. When your pods need more resources than the current nodes can provide, the CA is supposed to step in and add more nodes. Simple enough. But here's the catch, and it's a big one. The standard Kubernetes Cluster Autoscaler operates with a fundamental limitation. It can only scale predefined groups of identical server types. These groups are called node pools. So if you set up a node pool with, say, M5.large instances on AWS, the CA can add more M5.large instances or remove some, but it can't decide on its own. Hey, this new workload is really memory hungry. Maybe we should add a few R5.large instances instead. Or perhaps a mix of different types would be cheapest. It's stuck with this homogeneous scaling approach within the node pools you manually defined beforehand. Think about the sheer variety of virtual machine instances available from cloud providers like AWS, Azure, and GCP. You've got compute optimized, memory optimized, storage optimized, burstable instances, instances with GPUs. The list goes on. Each has different resource ratios and different price points. If your autoscaler can only add more of the same kind of node, you're potentially leaving a lot of money and efficiency on the table. You might end up over-provisioning CPU just because you needed more RAM, or vice versa. Administrators have to make educated guesses up front about which instance types might be good, configure node pools for them, and then hope for the best. The CA can't dynamically choose the optimal instance type, or, even better, the optimal combination of different instance types based on the actual, real-time demands of the workloads running in the cluster. This is precisely the problem tackled by the paper Cloud Resource Allocation with Convex Optimization by researchers at UC San Diego. They propose a fundamentally different approach. Instead of reactive scaling within fixed pools, they frame the resource allocation problem as something that can be solved mathematically to find the genuinely best, most cost-effective mix of diverse instance types. Their core idea is to use convex optimization. Now, if your optimization theory is a bit rusty, think of it like this. Imagine a perfectly smooth bowl. Finding the single lowest point in that bowl is relatively easy. Algorithms can do it efficiently and reliably. That's a convex problem. A non-convex problem is like trying to find the lowest point in a landscape full of hills and valleys. You might find a local low point, but it's much harder to guarantee you've found the absolute lowest point globally. By formulating the Cloud Resource Allocation Challenge as a convex optimization problem, the researchers aim for a solution that is both mathematically sound and computationally tractable. So how do they model this? They create a mathematical representation of the situation. The inputs are the resource demands, how much CPU, RAM, storage, maybe even network units your workloads collectively need. This is represented as a demand vector D. They also factor in the costs of different instance types, let's call that C, and how much of each resource each instance type provides, captured in a resource composition matrix K. The goal is to find the optimal number of each available instance type to provision. This is the allocation vector X, such that the total cost is minimized, while ensuring all resource demands are met. But it's not just about minimizing the direct cost, which is essentially the sum of costs C times the number of instances X. The researchers cleverly incorporate other real-world factors often handled qualitatively or through heuristics. One major factor is operational complexity. Managing a cluster with dozens of different instance types from multiple cloud providers can be a headache. To account for this, they introduce penalty terms into their objective function, the function they are trying to minimize. Here's where a key innovation comes in. They want to penalize using too many different instance types or spreading across too many providers. A simple way to model using more than one provider mathematically might be with an indicator function. It's 1 if you use more than one provider, 0 otherwise. The trouble is, indicator functions create sharp jumps, making the optimization problem non-convex, more like that bumpy landscape. Their clever trick is to use smooth, non-linear approximations. Specifically, they use a term involving e raised to the negative power of the number of instances per provider, e caret, beta 1 ex, to create a smooth penalty for provider fragmentation, where e maps instances to providers and beta 1 controls the penalty strength. This term approximates the indicator function while keeping things smooth. They also use a logarithmic term, log 1 plus beta 2x, to model potential volume discounts you might get from using many instances from a single provider, controlled by parameters gamma and beta 2. These smooth mathematical terms gently discourage diversity and encourage consolidation without breaking the convexity of the overall problem. This means they can mathematically balance the pure cost savings of picking the absolute cheapest mix against the operational desire for simplicity, and still find the globally optimal trade-off efficiently using standard solvers. They also include penalties for not meeting the resource demand D, and allow for some tolerance in meeting demands, represented by micro, and acceptable over-provisioning. G, making the model more realistic. The constraints ensure that the chosen allocation X provides enough resources, Kx, must be greater than or equal to D minus micro, but doesn't waste too much. Kx must be less than or equal to D plus G. To ensure they've got the math right, they derive the Karush-Kuhn-Tucker conditions, or KKT conditions, for their problem. For engineers, think of KKT conditions as the rigorous mathematical checklist that guarantees a solution is truly optimal for a constrained optimization problem like this one. It provides theoretical backing for their approach. Now, solving this involves dealing with the fact that you can't order half a server. The number of instances X needs to be whole numbers, or integers. While they relax this constraint, allowing X to be continuous numbers to achieve convexity, they ultimately need an integer solution. They discuss using techniques like branch and cut, which are designed for these mixed integer problems. The paper mentions using the GLPKMI solver, which implements branch and cut. This method explores potential solutions systematically, pruning branches of the search tree that can't lead to an optimal result. The paper also acknowledges other practical strategies like rounding the continuous solution or using multiple starting points to improve the search, although their reported implementation primarily focused on the branch and cut solver. Okay, that's the theory. Does it actually work? The paper presents results from simulations comparing their convex optimization approach against a simulated standard Kubernetes Cluster Autoscaler. They used real instance specifications and pricing data collected from Azure and Linode APIs, specifically 940 instance types from Azure and 940 from Linode, covering a wide range. They designed 5 different scenarios representing common Kubernetes use cases: a basic greenfield web app, scaling an existing app, a constrained enterprise environment with predefined node pools, a workload specifically needing high memory intensive, and a highly constrained scenario where only small instances with 2 CPU cores or less were allowed, but demand was high. The results are quite striking. While for the simple web app, both approaches had similar costs, the optimization approach pulled ahead significantly in more complex scenarios. In the scenario modeling scaling an existing infrastructure, it achieved 42.5% cost savings. For the enterprise environment, the memory-intensive workload, and the highly constrained scenario, the cost reductions were dramatic: 80.5%, 87.2%, and 71.1% respectively. For that memory-intensive workload, scenario 4, the standard CA simulation ended up costing $1.08 per hour, whereas the optimization approach found a mix costing only 14 cents per hour. The average cost reduction across all scenarios was over 56%. Why such a big difference? It boils down to resource utilization. The paper includes analysis showing resource over-provisioning. The simulated Kubernetes CA consistently over-provisioned resources because it was stuck scaling homogeneous node pools. The most extreme example was scenario 5, the one with high demands but restricted to only small instances, 2 cores or less. Because the CA had to use many small, potentially poorly suited instances to meet the total CPU and memory demand, it resulted in massive waste. The paper reported an average resource over-provisioning of over 13,600% for the CA in that scenario. In contrast, the optimization approach, free to choose the best mix even from those limited small types, kept over-provisioning much lower, below 2,300% across all scenarios, by selecting instances with resource ratios that better matched the actual demand. It confirms the core hypothesis. Being able to intelligently select a heterogeneous mix of instances makes a huge difference. So what does this mean for us engineers in the trenches? First, it highlights a significant potential inefficiency in how we currently scale Kubernetes clusters in the cloud. Relying solely on the standard CA with manually curated node pools might be costing us substantially more than necessary, especially for workloads that aren't perfectly balanced in their resource needs or in environments with constraints. This research proposes a path towards what the authors call an infrastructure optimization controller. Imagine a component in your cluster that continuously analyzes workload demands and cloud pricing, then proactively adjusts the composition of your cluster's nodes, not just the count, to maintain an optimal state. It's a shift from reactive scaling, where out of memory, add another identical node, to proactive optimization. Based on current needs and prices, the ideal mix is 3 of type A, 5 of type B, and 2 of type C. This aligns perfectly with the goals of FinOps, maximizing the business value of cloud spend. The explicit modeling of trade-offs like operational complexity, provider fragmentation, instance diversity, using those smooth penalty functions is also really interesting. These are often fuzzy concepts we handle with rules of thumb or policy. Quantifying them mathematically within an optimization framework allows for more principled decision-making. You could potentially tune the parameters, like alpha, beta1, gamma, to reflect how much your organization values provider consolidation or simplicity versus pure cost savings. Of course, this research is based on simulations, which raises some practical questions. How would such a system handle the messiness of the real world? Cloud environments are dynamic. Spot instances get interrupted, prices fluctuate, demand surges unexpectedly. The paper acknowledges this, listing dynamic adaptation and better modeling of spot and reserved instances as key areas for future work. The current model assumes static demand for the optimization calculation. Integrating predictive forecasting or online optimization techniques would be needed for production readiness. Another question is computational overhead. Solving mixed integer optimization problems can be computationally intensive. Is the branch and cut approach fast enough for near real-time decisions in a large, busy cluster? The paper notes the worst-case complexity can be exponential in the number of instance types, though the average case is often much better. There's likely a trade-off here. Perhaps the optimization doesn't need to run every minute, like the CA might check, but periodically, say, every few minutes, hourly, or even daily, to adjust the long-term node composition strategy, while faster mechanisms handle immediate pod scheduling onto existing nodes. How would this integrate? It seems positioned as a potential replacement or augmentation for the cluster autoscaler's node provisioning logic. It's important to distinguish its role. Horizontal pod autoscaler, HPA, scales the number of pods. Vertical pod autoscaler, VPA, adjusts pod resource requests. And the standard cluster autoscaler, CA, adds or removes nodes of predefined types. This proposed optimization controller would decide which types of nodes and how many of each should exist in the cluster for the Kubernetes scheduler and pod autoscalers to use most effectively. A significant limitation mentioned in the paper's future work section is the lack of explicit handling for high availability, or HA, constraints. Production systems often require spreading pods across multiple identical nodes in different availability zones for fault tolerance. Enforcing constraints like minimum 3 nodes of type 10 spread across zones adds significant complexity, potentially making the optimization problem harder to solve quickly. This is a crucial gap to bridge for real-world deployment. Despite these areas for future work, the core idea is powerful. By leveraging convex optimization, this research provides a mathematically rigorous framework for moving beyond the limitations of homogeneous scaling in Kubernetes. It demonstrates a clear potential for substantial cost savings and dramatically improved resource efficiency, especially as clusters grow and workloads become more diverse or specialized. It paints a picture of a future where our infrastructure doesn't just react, but intelligently optimizes itself based on demand, cost, and even operational preferences. It's a compelling direction for making cloud-native infrastructure smarter and more economical.